Yes, hello, welcome everyone to this session on real-world applications of recommender systems. We got 5 presentations in this talk. Please post your questions as usual on Woover, and we will try to read out those here in the chat. I'm Dietmar Jannach. I will chair this session here, and I think we're ready to go. So first speaker is ready. This is Shu giving a talk entitled Learning to Collaborate in Multi-Module Recommendation via Multi-Agent Reinforcement Learning without Communication. Please go ahead.
Okay, I will share my screen. Can you see it? Yeah, okay. Hello, everyone. I'd like to talk about my paper, Learning to Collaborate in Multi-Module Recommendation via Multi-Agent Reinforcement Learning without Communication. So this paper is a joint work of Nanyang Technological University and Alibaba Group. So we first introduce the setting and motivation of our work. In many e-commerce platforms, there are multiple modules on one page to recommend items with predefined properties, such as the items with 0% installment and special discounts. Different teams are in charge of different modules, and their objectives are the same: to get more clicks by users. Different agents with the same objective and individual optimization usually lead to competition and suboptimal global policy for the e-commerce platform. For example, there is reputation of items and categories in these two figures. The interactions between users and the platform is a sequential decision problem. Users can go to module pages and item detail pages, or refresh the entrance page to obtain their to obtain other recommended commodities. So we use multi-agent Markov decision process to model interactions. In MDP, modules are agents and users are environment. Agent ranks items based on users' features and obtain clicks as reward. A user feature will change according to their behaviors. The challenges in this process are that we need to mitigate competition between modules without communication, since modules need to recommend items simultaneously within a very short period. Many works apply reinforcement learning to recommender system domain. Their contributions can be divided into 3 cans. Some of them consider different kinds of rewards like return time. Some propose methods for the structure of web pages. For instance, take the whole page as input and consider advertising. Others focus on the huge space of commodities. Some clustering methods are used in such works. Only 2 papers apply multi-agent reinforcement learning to recommender system. They consider the sequential pages controlled by different agent. And thus, after users leave the first page, the first agent can send a message to the second one, and the second one acts based on both users' feature and the message. The difference is that we consider agents that act simultaneously without communication. Our idea is inspired from correlated equilibrium, which is a concept from the game theory. A simple example is the intersection and the traffic light. If there are 2 cars that want to go through the intersection, both of them can choose to go or stop. If both of them choose to go, they would crash and pay $100 to repair the car. If they both choose stop, they cost 1 minute to wait. But because of the huge loss of the crash, 2 cars are prone to choose stop according to game theory. Actually, it's about 99% to choose stop. However, this is not the optimal solution for the whole intersection. The best solution is to use the traffic light to tell them to go alternately. So in our paper, we introduce a signal network to send signals to different agents to maximize the overall reward. Additionally, an interface regularized version is proposed to promote exploration. We also implement experiments based on the dataset from Taobao, which is one of the largest e-commerce platform in the world. The architecture of our method is shown in this figure. Our method is based on actor-critic algorithm, which is popular in reinforcement learning. There are three components: the signal network, actor, and the critic. The input of the signal network is the user feature, and the output are signals to promote cooperation. The actor is used to rank items given user feature and signal. The critic aims at estimating the cumulative reward obtained by the output of the actor and provide a gradient to actor. Here is a detail of these three components. Each of them includes a state embedding module to get the embedding of different users. The features of users can be divided into two types. Static features include gender, age, and other fixed properties. The sequential feature consists of a feature of historical clicked items. We use attention mechanism to get the embedding of a sequential feature by learning the weight of historical items. For the ranking part, our actors output a vector as the weights of elements in item feature. We use an embedding layer to get item feature and then use the weighted sum of action and the feature as scores of items. For each agent, we apply soft actor-critic algorithm to update parameters, which adds an entropy of positive pi to encourage exploration. Each agent aims at maximize their own reward. For the signal network, the objective is to maximize the overall reward. However, the policies of the agents are changing over time. So we propose to use the interface regularized version of update to explore how to choose the best signals. By this way, our algorithm explore more before convergence, which is shown in this figure. The shaded range shows the best and the worst performance in multiple ranks. Algorithm without the interface term doesn't tend to explore during training. In our experiment, we use NDCG and precision as metrics. We use 14-day records as training data and 3-day records as testing data. In each record, there are 10 candidate items for each module. The task is to re-rank these 10 candidates, and the clicked items should be ranked higher in each module. We use supervised learning method, reinforcement learning method as baselines, and also two methods for ablation study, which is our algorithm without attention and interface term respectively. Here is a result of the offline experiment. We classify baselines considering their properties. There are two single agent method, some multi-agent method, and then we apply soft update for actor and critic for this multi-agent reinforcement learning method, and finally our algorithm with the signal network and the soft update. The results show that our method outperforms other baselines. Due to the huge cost and the risk caused by deploying different algorithms to the real-world scenario, we build a simulated online environment. A simulator is used to simulating users' interactions. Given the recommended items of two modules, the simulator provides the CTRs of these items. In this way, the interactions of modules are considered. In this setting, we store 2,000 candidate items for each module, and each agent recommends 3 items. We train our model by 30,000 steps and get the results by 10 runs. The bar graph shows the results of all the algorithms. The results in the red box are the performance of our algorithms, including the ablation study. Again, we illustrate that the interface term prompt exploration before convergence. So in conclusion, we first model the multi-module recommendation as multi-agent reinforcement learning problem. We then design a signal network to maximize the overall reward. Thirdly, we propose an interface regularized version to coordinate agents exploration. Additionally, we implement online and offline experiments based on the data set from top. So that's all. Thank you.
Yes, thank you very much for these nice presentation of a really interesting practical questions. I hope we see more work on this in the future. So we have time for a few questions. While we just wait, let me just ask you a question, a non-technical one. So one part of the problem is that the teams that develop the components of the website do not cooperate, right?
Yeah.
So wouldn't that be an easier solution to have them cooperating?
So in our paper, we use, let me check the slides. So in our paper, we use a signal network to maximize the overall reward by sending the vectors to each agent. I think that in this way, the performance of the algorithm improves a lot in our experiments, but there is a challenge here is the policies of each agents are changing over time. So that means that if training our signal network find a good way to send signals to each agent, if their policies are changing, the good signal will probably become bad during the time. So we use the interface term to light the signal network to explore more, to choose a good way to send signals to each actors. Besides our method, I think there are many methods in reinforcement learning consider multi-agent cooperation problem, such as the baselines we used in our experiments. Also, they found some way to let these agents to cooperate, but their performance is not very good in recommender system. But maybe in other domain, their performance is good enough. But in our experiments, our algorithm performs the best. Yeah, thank you.
Another question is, so you're using simulation. What? It's not possible to run an A/B test, or how close is your simulator to the real world? Can you make an estimate?
So, as I said, due to the huge cost and risk caused by deploying different algorithm to the real world, so we choose to use a simulator. Our simulator uses the whole page as input to simulate the interaction between each modules, which means that if the recommended items of the first module changes, then the recommended items of the second module are affected by this change. So we use the whole page as an input to our simulator to model this interaction, and also we use the user feature as an input to get more access results. And our simulator will output the CTRs of items, so we can use these CTRs to evaluate our algorithm. Yes, thank you.
Okay, one quick question. There's one question: how many iterations and time do you need to warm up the model? When do you say that the model is trained enough? Asked by David.
Okay.
A quick answer, please.
So you can see it in this feature, in this figure. we use about 5,000 steps to let our algorithm to converge. But in the beginning, the performance of our algorithm increased very fast, and to get a relatively good performance. Yeah, thank you.
Okay, thank you very much again.
Yeah.
Thanks for the presentation. And we can move on to the second paper. So this is presented by Liu. The paper is called Exploring Clustering of Bandits for Online Recommendation System.
Okay, I will start share. Okay. Hi, everyone. In today's presentation, I will introduce our work, Clustering Explorable Bandit for Online Recommendation System. This presentation can be divided into 3 parts. In the first 2 parts, we will briefly explain online recommendation system and its problems. And then we talk about the existing solutions using bandits. Then in the last part, I mainly introduce our new bandit policy, its experiments and regret analysis. So online recommendation system is one of the most popular application areas of machine learning. It customizes personalized recommendation services like articles, music, or short videos for each user. And the system receives feedback such as clicks, comments, and likes from users. The target is to accurately dig out the interest of users from their behavior data. Thus, the recommendation system could show them the desired item to make a profit. However, the traditional recommendation system always suffers from the exploitation and exploration dilemma. In the absence of exploration, supervised learning algorithms tend to get stuck in the suboptimal solutions. And Bandit is a classic approach for solving this dilemma. It describes such a situation. Imagine you are in a casino and there are lots of slot machines with different probabilities of winning, and how to play for the most money. Should I always pull the arm of the known most profitable machines, or should I try new machines? The recommendation scenarios is just the same. Should I always recommend the most popular articles to users, or should I try to push new articles? The target is to obtain the highest long-term rewards. And the contextual bandit algorithm has been studied for years to solve this problem. In a contextual bandit setting of online recommendation system, articles and their corresponding features like title categories are observed by the agent. And at each step, the agent chooses one article to present to users according to their click histories. And the agent tries to know about user interest from the received finite and noisy rewards. Therefore, the learned parameters contain uncertainties. Taking those uncertainties into consideration, the contextual bandit prefers a known atoms with high CTR, which is the exploitation. And in the meantime, the contextual bandit policies also tend to choose the atoms with large uncertainty, which is the exploration. However, contextual bandit algorithm suffers from cold start problem facing insufficient data. To alleviate this problem, class of bandit policies have been started for the last few years. In this algorithm, each user maintains a separate set of parameters, and users are divided into different groups using clustering techniques. They incorporate collaborative filtering effects into bandit methods for enhancing performance. In the view of transfer learning, collaborative filtering shares knowledge among similar users and atoms. However, this algorithm introduces another kind of uncertainty, which is the uncertainty of clustering, and they all ignore this uncertainty. And for our proposed bandit policies, clustering explorable bandits, which is the Klex bandit, consider both the uncertain estimation of user interests and the uncertain user clusterings. On the one hand, Klex bandit estimates user clustering more accurately with less uncertainty where explorable clustering. On the other hand, ClaxBandit also exploits and explores user interests by sharing information within and among user clusters. In summary, ClaxBandit explores knowledge transfer and further easy inferences about user interests. And the detailed problem setting is: suppose there are n users, and at each time step t of the online recommendation, the agent faces one user and its arms with context, with features. The agent will choose one article to recommend, and then the agent obtains the feedback of this article from the users. And the objective is to select proper actions from A1 to AT, and to minimize the cumulative regrets, RT. And our methods can be explained in two parts. The first part is knowledge sharing with where adaptive clustering. We hold the linear assumption of each user. X is a feature of the arms, and theta is a linear parameter of users, and eta is a Gaussian noise. And there are several interest clusters. One user's parameter vector can be a linear combination of several parameter vectors of clusters. The capitalized theta here is generated by stacking the user parameter vectors, and L stands for the d-dimensional parameter vectors of interest clusters, and S represents the proportions of user holding each interest. Also, we assume S is sparse, which means users' interests do not cover all the interest aspects. And the sparsity of S can be achieved by adding extra prayers on S. And the second part of the approach is learning user interests via exploring clustering. We follow the Thompson sampling solution, linear Thompson sampling, to spotify the adaptive clustering with exploration. At each time step t, we sample tilde L and tilde S from the corresponding prayer and prayer distribution, whose means and covariances can be calculated via alternately fixing S and L. After we get the tilde L and tilde S, we could give a prediction for each arm. The arm which gives the largest prediction will be chosen to recommend. And our experiments utilize the replay offline evaluation method, which construct the data stream from the log data of online random policy. We compare our model with 5 baselines: ClaxBandit dense, which is the ClaxBandit without sparsity characteristics, and then CAB and SCLAB. They use different clustering techniques to cluster users. And the last two is linear Thompson sampling local, which is we hold a separate parameter for each user, and there is no knowledge sharing among these users. And linear Thompson sampling global, which means we only use this one global linear Thompson sampling model to serve all users. And besides, we have a warm start period in the beginning. ClaxBandit and ClaxBandit dense will degenerate into a linear Thompson sampling local in this period. Then they will use SVD for initialization after the data communication. And first, we conduct the synthetic experiments where the data is created conforming to our assumption. In the left figure, we plot the cumulative regress with regard to the number of steps. And as we can see, ClaxBandit outperforms all the other algorithms on synthetic data. The reason is that ClaxBandit fits our assumption perfectly. However, the other 5 baseline models validate the assumption more or less. And the right figure illustrate the sparsity pattern of S that is required under different degrees of explorations. As we could see, the more we explore, the more accurate sparsity pattern we could capture. And Another two observations in the synthetic experiments are, first, the model will converge fast if the true number of user clusters is small. And the second is if there exists no sparsity patterns behind the data, which means the data is violates our assumption about the sparsity characteristics. As we could say, Kleck's bandit could stay very close to Kleck's bandit dance. But is still inferior to it because Kleck's bandit spends extra efforts on exploring the sparse parameter structure at the very beginning. And we also conduct experiments on industrial data sets. The first is the Last.fm dataset. The Last.fm dataset is a public dataset, and another dataset is WeChat data. Which is obtained from the online recommendation services in WeChat, Tencent, which is company in China. As we can see, our approach, Kleck's bandit, also outperforms the baseline models in the long run because of the additional exploration of user clustering. And last, we provide the regret analysis. The call is to prove that the prediction is concentrated around the respective mean. Since it's not a jointly convex problem if we optimize L and S together. Therefore, we investigate by solving them separately. According to the theorem, Kleck's bandit enjoys the same order of sublinear regrets as a linear Thompson sampling. And one important reason is that Kleck's bandit need to explore a smaller parameter space compared with the baseline models. And that's all. Thank you for watching. Is there any questions? Hi. Oh, you can hear me? You cannot hear me. Sorry.
Sorry. Can you hear me again now? Oh, sorry, something happened here. Yes, thank you for the presentation. The first question is, what's the difference of the clustering method used in your algorithm and the baselines in the experiments?
The difference is the clustering method using the baseline models is heuristic. It means it cannot be optimized, and my clustering method is adaptive clustering method. It can be optimized by the loss.
Okay, thank you.
Mm-hmm.
Other question, one is maybe, since this is the real-world applications track and there are a number of authors from industry on this paper, it would be really interesting to see how this works in the real world. Do you have any plans to test this in a real setting?
So first we use the data set from WeChat. WeChat top stories is recommendation applications in China. But the updating frequency of the recommendation system, of modeling the recommendation system is 1 day. Per day, it will update the model. So it's very hard to really put our models online because our model is an online learning model. We need to update once we receive feedback from users. So for now, we cannot put it online. But in the future, we want to put it online to see the results.
Mm-hmm. Okay, one last question, which is maybe naive. So when you optimize in your simulation experiments, you look at the regret, right?
Yeah.
How can we interpret this on an absolute scale? So you outperform your baselines on this regret, but what does it mean, right? Is it useful at all on an absolute scale? Just a quick response, please.
Okay, so we use the communicative regress because our baseline model, the previous works use this evaluation metric. So we just use this metric for comparison. So we also have a lot of other metrics about RMSE, but we didn't show it here. So.
Okay, there was one quick question with yes or no. Will the WeChat data be publicly available at some stage?
No, the WeChat is not public data set. So because of that, so we use another public data set, the Last.fm.
Okay, good. Thank you very much again.
Thank you.
And we can then move on back to Shu for the second presentation, or the third in this session, which is contextual user browsing bandits for large-scale online mobile recommendation.
Yeah, thank you. So hello everyone, it's me again, this talk is about our paper, Contextual User Browsing Bandit for Large-Scale Online Mobile Recommendation. I'd like to thank my co-authors, and this paper is a joint work of Nanyang Technological University and Alibaba Group. So we consider the recommendation task in mobile devices when a user opens a page, an algorithm selects a list of items to show in this scenario. Due to the limited screen size, users can only see 2 items in the screen, and they need to slide the screen to browse more items. In this process, some items are actually not being viewed by the user. Consider a simple example shown in the figure. A user clicks the first item and then closes the app. Then the items below the second one are not viewed by the user. And for the second item, we are not sure if the user noticed it or not. However, although the user doesn't click items below the second one, they are all labeled as negative samples in our dataset. This phenomenon is very popular. So in our work, we model the recommendation task as a contextual bandit problem. Recommended items and clicks are arms and payoff in bandit problems. The algorithm needs to recommend items to users and get feedback from users. There are mainly 2 challenges, as we mentioned in the example. The first one is the position bias, that higher positions lead to more clicks for the same item. We call another challenge shadow exposure, which means that we do not know exactly whether recommended items are viewed or not. Items that are not viewed shouldn't be labeled as negative samples directly. In the pie graph, we can see that only 6.2% clicks are at the last position in our dataset, which suggests that only for this data, we know that users viewed all items. Thus, shadow exposure issue affects most of our data. Our work follows the citing of a combinatorial bandit problem, where a set of items are put in each round rather than only one item. There are some works that apply different click models in this citing. However, they either ignore the influence of positions or fail to use context. Moreover, they do not consider the shadow exposure issue. Our contributions are fourfold. First, we apply a new click model considering position bias and shadow exposure. Second, we use context to improve scalability. Then we provide theoretical analysis for our proposed algorithm. We also conduct both offline and online experiment based on Taobao. We first introduced the UBM model. In the above-mentioned process, we consider what can be used to address these 2 challenges. For each record that including all the recommended items and clicks, we know the positions of items and the clicked items. Thus, we can use this information to estimate the influence of position bias and shadow exposure. We use the user browsing model to estimate the examination of users, which is the probability that an item is viewed by a user. The UBM assumes that examination depends on both position and the distance to the last click. We use W to represent the examination. The subscript K and K prime indicate the position of an item and the last click. For example, if a user clicks the first item, the probability that he views the second one is larger than the third one. Then we combine the UBM with LinUCB, which is a popular Bandit algorithm. Our algorithm has four key parts: select parameter, compute upper confidence bound, select items, and update. LinUCB uses upper confidence bound to estimate the attractiveness of an item, which is mean plus a standard deviation. To obtain estimate of the mean and deviation, we use the online version of ridge regression, whose objective is to minimize the loss function, which is a MSE loss plus a regularization loss. To select the best parameter and the optimal recommended site, we do the theoretical analysis. Similar to previous work, the objective is to minimize the regret, which is a gap between rewards of the optimal site and sites selected by the algorithm. The reward function is the probabilities that users click at least one item, which also follows previous works. We first prove that given a list of items, the order that maximize the reward is to rank items according to their attractiveness from high to low. In the theorem 1, we prove the sublinear cumulative bound for our algorithm and indicate how to choose ARF to achieve this sublinear bound. So we also use this value in our algorithm. We implement online experiments based on two datasets, a public dataset, index dataset, and a dataset obtained from Taobao. We first propose an unbiased estimator to remove bias based on assumptions of UBM. The idea is to use examination probability to estimate the true probability of clicking. Following previous work, we assume that W only depends on the page structure, which not changes in a long period. Thus, we can compute W by historical data. For features of items, we use SVD to decompose the user website metrics to get context for the index dataset. Since this dataset doesn't include features of items, for the Taobao dataset, we build an autoencoder to reduce the dimension of the original feature from 56 to 10 because the computation complexity and the bound is related to the dimension. For the baseline, we compare with other click models used in previous works. The offline task is to rank historical data, which is selecting K items from 20 and 12 candidates for index and top dataset, respectively. We use two metrics in the experiment. The first is probability that users click at least one item. The second is a sum of clicks. The results of for two datasets are shown here. We change the number of recommended item K from 3 to 6. The algorithm that doesn't use any click model performs worse with the increase of K. We also implement experiments based on the real-world testbed in Taobao. We use A/B test where users entering our scenario will be randomly divided to different algorithms. Each algorithm needs to select 12 items from 40,000 candidate items for millions of users per day. The flow of our online experiment is shown in this figure. Each algorithm will update based on real-time logs. The parameters are stored in the online key value system and used to rank items when a user enters. The results of the 3-day experiment are shown in the figure. The first figure is a change of CTRs over time, and the second is total CTRs each day. So in summary, we first model online recommendation as contextual combinatorial bandit problem. Then we combine UBM with contextual bandit algorithm and propose a novel algorithm. We also prove sublinear expected cumulative regret bound for our algorithm. Additionally, we conduct both online and offline experiments to evaluate our algorithms. Thank you. That's all.
Yes, thank you very much for this presentation. Very nice. Good to see that you could do online experiments as well. Good. Here's one first question from Q&A session. So in the real world case, do users behave more like DCM or UBM?
DCM or UBM. I think for the experiment result, you can see that our algorithm performs better than the method used DCM by these two figures. The orange line is our algorithm, and the green line is DCM model plus linear CB algorithm. So I think the UBM model is a little better for online experiment. And to model users clicks.
Okay. Another question is, so there's another one. The question is, how would you benefit if you could have impressions data of viewed but not clicked items?
Okay. If a user didn't click an item, we actually use the W here to estimate the probability that a user viewed an item or not. If the user viewed the item and the user didn't give the click, it means that he doesn't like the item. So we can use this item as a negative sample. However, if the user doesn't see the item, we cannot use this data as negative examples directly. So we use W here to estimate the probability that the user can see or can view or not view the item, and then use this as a weight to evaluate the data and to update our algorithm. Yeah, thank you.
Okay, so we have a number of questions. I think we'll not go through all of them here, so please then look at the Q&A. Let's do a few more. Question three is, did you look at shifting user behavior and whether the optimal recommender would thus change for them over time?
Not sure. I think the Bandit algorithm is an online learning algorithm. So for the scenario that items and users change very fast, I think Bandit algorithm can perform much better than the other type methods such as supervised learning method. But otherwise, for the scenario that the items and users are relatively static, I think supervised learning would be better. But for our scenario, I think Bandit algorithm is better. Yeah, thank you.
Okay, I have one here about the online experiment. Can you explain a bit about the architecture used for the online experiment? Not too detailed, please.
Okay.
About the architecture.
Yeah. So the parameters of different algorithms will be stored in the online key value system and to rank items if an user enters our scenario, and the clicks of these users and the recommended items are stored as logs And then we use these logs to update our Bandit algorithms to make sure that the performance can be better. Yeah, thank you.
Okay, so there are more questions. Yes, again, please use the session Q&A. Thanks again to the speaker. Thanks for the presentation. We can then move on to paper presented by Mavulolo. It's called Offline Contextual Multi-Armed Bandits for Mobile Health Interventions, a case study on emotion regulation.
Can you see my slides? All right.
Please switch to presentation mode. Yeah, thanks. Sorry.
Okay. Hi, my name is Mawololo Ameko, and today I want to present to you our work on offline contextual multi-armed bandits for mobile health interventions, a case study on emotion regulations. And my name is Mawololo, and this is joint work with our colleagues from the psychology department. So you might ask yourself, what is emotion regulation? Well, a generally accepted definition of emotion regulation is a process by which individuals influence which emotions they have and when they have them and how they experience these emotions. And so some of the examples by which we regulate our emotions from day to day is, for example, eating a lot or something called emotional eating. Doing some activity outside to make ourselves feel better, or binge watching funny YouTube videos online, and probably even listening to sad music to make ourselves feel better. So you might ask yourself, why do we really care? Why do we care about something as mundane as emotion regulation? We all do that. It turns out that in the psychology literature, it's been shown that flexibly applying different emotion regulation strategies in different contexts is associated with psychological well-being. And so clinicians really, really care about the process of emotion regulations because it has, large ramifications on how, our mental well-being is in the long run. And also, we know that emotion regulation strategies vary in effectiveness for different people in different contexts. And so the idea is that if we can build an emotion regulation recommender algorithm, we can then scale that through smart devices to help people to better regulate their emotions. So what is the aim of this work? The aim of this work is basically to build an algorithm to recommend emotion regulation strategies that will be effective for any person in a given context. So how do you achieve that? We have a bunch of data that is logged already from a past study, where we had 114 individuals with high social anxiety, aged between 18 and 45. And this study was conducted over a period of 5 weeks, where each participant had an application installed on their phone where we could stream data from these applications, from different modalities, namely the actively sensed data and then the passively sensed data. Some of the actively sensed data is actually, what we call ecological momentary assessment, or surveys that we send to each individual's daily, 6 times in a day. And some of the passively sensed data include location data from GPS, activity data, and activity level from accelerometer, and so forth. Some of the activity types include, whether the person is cycling, whether the person is running, or whether the person is driving, or something of that sort. So we cast the problem of emotion regulation as in a mathematical framework of contextual bandits, which is a sequential decision-making problem, where we define the states, the actions, and the reward. Now, the goal of this work is to learn an initial policy which we can then deploy in the world or deploy online in the online setting. Why do we care about doing this online, learning this initial policy first? The reason is that first of all, clinicians don't know how to actually start applying this kind of technology through mobile phones, and they would like to know, first of all, that anything that we can learn is better than what people are already doing, and then we can carry the policy into the world. And so what are some of the states variables that are included in this work? Examples are, for example, like I said before, the GPS location of the person, whether the person is at home, in school, at a mall, or etc. The social context of the person, for example, whether the person is with family or friends, and whether the person is doing some activity outside or within, or cycling, or being in a car, for example. And what are some of the actions included in this work? We included 10 most frequently used strategies, which we call adaptive strategies. Basically, adaptive strategies are strategies that are seen to be recommendable, or some strategies that you would like to recommend, or psychologists think are recommendable. And some of the examples of such strategies are seeking advice and comfort from others, thinking about situations differently, coming up with ideas or plans for actions, and of accepting your emotions. And so these are some examples. We have about 10. We have 10 strategies that we are considering in this work. And our reward is defined as a binary vector, basically above and or below the perceived effectiveness, the ground mean of the perceived effectiveness. And so we have a 1. We have a positive feedback if the perceived effectiveness is above the ground mean, and negative feedback below the ground mean. So we explored a number of offline policy estimators, namely the direct method, the inverse propensity weighting method, and then the doubly robust method. It turns out that none of these approaches are guaranteed to work really well for any data, for any sort of data before you actually apply them. So we explored all of them because they each have their advantages and disadvantages. For example, the direct method, for example, is very low variance and very high bias. And the inverse propensity weighting is very high variance and low bias. And in high variance in the sense that, for example, in the denominator, you are likely to have very low values for the behavior policy or the propensity score. And so one way that is regularized is to cap off the very low propensity scores with some thresholding parameter like tau in this case. And we have the doubly robust, which balances between bias and variance, and it's a consistent estimator. So when we explore these approaches that we are proposing for this problem, we want to benchmark these approaches against the random and then the observed policy. The random is basically what you by randomly selecting any action or any strategy at all. And observed is what the people are actually already doing. And we want to be able to make sure that we are doing better than what the people are actually already doing. So some of the analysis choices that we've made include using the logistic regression as a value function approximator and estimating the propensity score, the behavior policy, using generalized boosted model. And we perform a 5-fold cross-validation for policy evaluation. So these are some of the results from our experiment. Turns out, well, in the first column, you see that the competing algorithms, the doubly robust method, the direct method, the offset tree, the OT, the offset tree, that is the method that is dependent or that relies on the inverse propensity weighting. And then we have the observed and the random. Turns out And also, these are results, these are values from the mean reward, evaluated based on the eve-expensive weighting at different thresholds, which we vary between a certain interval from 0 to 1 over the number of strategies that you're actually considering. So it turns out that the doubly robust method performs better than all the competing approaches and significantly better than the baselines, the observed, or maybe what the people are already doing, and then the random. So that is nice. But the clinicians actually want to know, what can we learn from this study for future studies? Say we were constrained resource-wise. What features do you care about, or which features were most significant in determining the effectiveness of strategies? Turns out that the timeliness of surveys are important. The activity the person is doing in context is important, and then the motivation of the person to change his feelings is also very important. And also baseline social anxiety scores are determinants in the effectiveness of strategies. So what are some of the limitations of our work? We assume that all the confounding variables are observed, which is almost always not true for observational studies. And there is, we assume that there is enough overlap. And in this work, we optimize for short-term immediate effect of strategies, while you can argue that there is a sense in which strategies have long-term effects on outcomes. And we approximated a behavior policy with propensity scores, which is not the ideal way of doing things if we had a behavior policy, but that is the constraint of the data. And future directions will involve modeling the the affect states in real time, and for a richer state representation, and developing approaches that are robust to unobserved confounders. So in summary, emotion regulation strategy effectiveness is context dependent, which we've shown in this work. And we were able to learn and evaluate policies, or an offline policy using log mobile data in a contextual bandit framework. Thank you.
Okay, thank you very much. An interesting problem. Hope to see or hear more of this in the future. Here's one question from the Q&A session. Could you explain more about positive feedback, the reward? I think there are two steps. One, users conduct the recommended ER strategy. Second, the strategy really works and the emotion is actually regulated.
Yeah, so, well, I like to first of all mention that this work is entirely in the offline setting. And so we are not doing an active experimentation of recommending strategies. And we have data on what the people reported to us as, the effectiveness of the strategies that they've used. And so we were constrained to using that effectiveness score to define the reward. And so we define the reward as, like I explained earlier, as a binary vector. Basically, you threshold the effectiveness score, which was a score on the scale of 0 to 10. We threshold that on the mean, the grand mean of the effectiveness, and defined anything above the grand mean to be positive and anything below to be negative.
Thank you. Another question is, how are context features represented in the model? Could you provide some examples?
Absolutely, yeah. So some examples of context features include, the person's location, GPS location, whether the person's at home, school, shopping mall, or a religious place, for example, and activity levels are defined from accelerometer features, and activity types, whether the person is running or whether the person is automotive or jogging, for example.
Okay. I think we have to move on to the next presentation. Thank you very much again.
Yeah.
Thank you. So, and the final presentation will be given by Ram, The title is Building a Reciprocal Recommendation System at Scale from Scratch, Learnings from one of Japan's prominent dating applications.
1 second, I'm just getting this up. Yeah, so share screen. It's up, share. Can you see this?
Yes.
1 second, I'm sorry, I'm not able to see this. Share screen. Yeah, share. Is it better now? Can you see this?
Very good.
Yeah, okay. Hi, everyone. Today I'll be talking about a recent project we worked on, building a reciprocal recommender system from scratch. And I'll be sharing our learnings from the process. This is joint work between Matching Agent and SBX. And my name is Ram, and I'm from SBX Tokyo. So Tapple is one of the leading dating applications in Japan that connects young people by their hobbies and interests. Started service in 2014, Tapple has over 5 million registered profiles. Until date, Tapple has made 200 million successful matches so far, which is the largest in the Japanese market. So once inside the app, people are shown profiles of the opposite gender, to which they can swipe left to like and right to pass. And when two users like each other, it's a match, and matched users can start a conversation by exchanging messages. Our goal here is to maximize the potential for mutual likes or matches. So designing a recommendation system for such a large-scale online dating system is complex and challenging for a number of reasons. First, as you might have seen, recommending people is not just unidirectional. It's equally important to recommend other target users who would reciprocate the subject user's interests. Second, people are dynamic. Consider the scenario between three people, Shun, Manami, and Saki. Initially, Shun is first recommended Manami. Shun likes her, but for some reason, Manami decides to pass Shun. Depending on this feedback, Shun broadens his preferences and likes Saki, who likes back, and it's a match. Thus, users' preferences evolve over time. It could also turn out the other way if the user receives more positive or favorable responses for their likes, their preferences might become more selective. And third, we observe that the interaction network is highly sparse and users are very selective about their preferences. Hence, in addition to solving the information overload problem, reciprocal recommender systems should be careful not to overload the users with poor recommendations, as rejection directly impacts user retention for the app business. So to model the mutual preferences, we start from a data-first approach. In conventional dating apps, people usually look for that one single match and they're done. But in our setting, we observed a significantly high number of matches per user. What you see here on the right is a scatter plot showing the distribution of matches per user, where on the x-axis shows the number of matches in log scale, the y-axis shows the number of users in log scale, and each point on the scatter plot shows the counts of matches per user, and this distribution shows most users have a significantly high number of matches. We wanted to build on this insight to develop models that learn useful embeddings of people that exploits this match information. So we first clean the data set to remove users with missing or invalid data or spurious data and filter users who are active in the last n days. We have the interaction data now and the user profile metadata as well that has information like location, users' interests, and so on. And once we have this, for training our models, our framework has all the usual collaborative filtering algorithms that we have discussed in this conference so far, be it matrix factorization, learning to rank, and neural network-based methods to generate the top-tier recommendations. I'm not going to go into the technicalities and the math behind the models here. The idea is to show the process and the impact. We use match interactions as positive samples and the interactions where if one of the users has passed the other user as negative samples. For inference, for a given user, we compute their preference vector based on their past matches and retrieve their nearest neighbors using an approximate nearest neighbors algorithm that runs in sublinear query time. So we note that the quality of our embeddings is not sensitive to the choice of the approximate nearest neighbors algorithm here. And for new users, we generate a pseudo embedding from the embeddings of users who have similar profile metadata, which is collected at the point of registration as the new user. But then we found not all users had enough matches to model their preferences with high quality. On the other hand, likes, even though unidirectional in nature, contain a richer fine-level representation of users' preferences. This meant we had to deal with 100 times larger training set in terms of the number of interactions. There was this interesting paper from last year's RecSys along this idea, which is basically to learn the unidirectional preferences from males to females and females to males separately, and then use some kind of aggregation function like harmonic mean or cross ratio uninorm to derive the reciprocal preferences. We adopted this bidirectional preferences learning approach and fusing them to fuse our unidirectional preferences learned from likes. And in this slide, we share the results from our approach. For offline evaluation, we use standard matrices like precision, recall, and F1 score. We take 1 month's data as training data and subsequent 1 week's data as the test data. Our method gave a 27% increase in recall over the previous matches-only model. But we all know offline evaluation is not representative of online performance. So we use engagement and conversion as matrices to evaluate online performance. First, measuring the short-term objective in terms of user engagement, we basically look at the likes. So it's the fraction of swipes which convert into likes. And for the long-term objective, we look at the ratio of matches to likes. So the bar graph here on the right shows the results of the online performance. While our method improved on the engagement, we still found it was not resulting in the conversion of likes to matches. After analyzing the logs, we found this was due to users who were not active at serving time. So when a user, by active, we mean so when a user liked another user, but if the other user is not responding, this recommendation was basically not converting. We had to debias to balance trade-off between 3 kinds of relevant users, recently online users, and newly registered users. And once we fixed this with a re-ranking solution, we found a significant jump in performance. So to formalize the end-to-end setup, we adopted the classical 2-stage information retrieval pipeline, which is basically the first candidate generation stage. We generate a few hundred good candidates, optimizing for precision from hundreds of thousands of users using collaborative filtering algorithms. And in the second stage, we do online re-ranking, optimizing for recall. And the objective here is to balance multiple objectives to recommend recently logged in users, newly registered users, and also debiasing against recommending popular users who have lots of likes and matches. So to put our system in production as a small team within a short time frame, we had to overcome a number of challenges. We split every independent component, be it the pre-processing, training, and the inference components into different microservices, and we built a distributed workflow so every new model we develop can be easily deployed and tested. But the pre-processing routines and the training algorithms and for the different models and the inference algorithms would have different environmental requirements. So we use Docker to containerize each of the microservices here. Next, keeping the models always online to serve recommendations would be expensive. We pre-compute the recommendations and store it in a high throughput, low latency distributed key value store. So recommendations can be retrieved in sub 100 milliseconds query time. And then transferring the recommendations generated from the AWS instance to the distributed key value store again would take hours. So to tackle this problem, we first split the entire recommendations dataset for all the users into smaller chunks using an SQL query engine and store it in a distributed data store, and then spawn multiple Spark workers which upload the data in parallel to the distributed key value store. Finally, error handling and data access patterns have to be streamlined for each of the microservices as they become more complex. We use AWS step functions, a serverless orchestrator, that would trigger each step containing a microservice sequentially in an event-driven workflow. Here is the end-to-end workflow summarized in one single slide. Aggregated input data in the form of likes, passes, matches, and user metadata triggers our algorithms, and these algorithms retrain the user's embeddings periodically. For warm start users who are already in the system, a batch job generates top key recommendations and spawns multiple Spark processes that copy the recommendations from the cloud storage into the distributed key value store like Amazon DynamoDB. For cold start users, we have an always on instance with all the model artifacts ready that serves as a streaming endpoint. For every new user, we create a pseudo embedding for them that generate the recommendations. By using AWS and its serverless infrastructure, we were able to build this with significant time and cost savings. To summarize the key learnings, we realized that making recommendations solely based on past interactions is not enough. By balancing the trade-off between relevance and recommending potential partners who are recently active, we could get better results for our users. Users' preferences change with every interaction they have with the recommendation system based on the feedback they receive, and it's important to update the embeddings and recalibrate the model parameters frequently. And finally, containerizing algorithms into microservices and orchestrating them into an event-driven workflow goes a long way in scaling our models. Thank you. And finally, we would like to thank our collaborators, and thanks for coming to the talk.
Yes, thank you very much for this presentation. Very interesting. While we wait for questions from the Q&A session, I think you mentioned that there's this issue that some users are very popular, so everyone wants to connect with them. I didn't get how you deal with the problem. Mm-hmm. Or is it implicitly handled?
So one way to handle this is either you tackle this at the collaborative filtering stage where you train your offline models, or you can tackle this at the online post-processing stage. So in term, when you tackle this when you see bots or spurious users who have an obscenely large number of interactions, you can easily remove them by observing whether they are divergent from the general data distribution at the collaborative filtering algorithm. And it's at the online re-ranking stage, you basically have different parameters, or you can have a linear model where you weight the different parameters like new users or recently active users or popular users and tune your models accordingly.
Mm-hmm. One question here is how frequently you need to update the user embeddings?
So this depends on the use case. So sometimes there is some campaigns which are being run, and for sometimes it also depends on whether the male to female interactions and the female to male interactions, how vast is the difference between the distribution. So often in our setting, we observe usually the males who are very active and have a lot of interactions or likes towards the female users, while the female users are mostly reactive. So in that case, it's very important to update the embeddings periodically, because especially in case of female users who are reactive, their behavior would change with every interaction they receive. The actual time frame is depending on the model in production. We need to tune it based on what we see, how the model is performing and monitoring every time.
Okay. I have one more question. So you use different metrics for online and offline. Mm-hmm. Did you find a good offline metric that could serve as a proxy for the online success?
That's a good question. So in our setting, we generally see the response for the likes which a user sends is more important. So usually in some dating apps, it's usually double blind, where one of the users likes another user and the other user is not given any notification. In our setting, it's whenever a user sends a like, the other user gets a notification and they could either respond or pass. So in this setting, I think it's hard to have a good proxy for online metric where the users how active the users have been in recent times is very important. But you could have some way like coming up with an environment where you simulate users' recently active data points collected from online evaluation into an offline experiment, controlled experiment, and look at the models and so on.
Okay. We have a few more questions. Let's try how far we get. So next question is, for the users with few matches, have you analyzed whether the likes or the passes are what gives you more information about them?
So generally, we find that the richest information is present of users' taste is in the likes. The users dislikes also hold significant information, but it's a balance of how much hard negatives from the dislikes you want to sample. So the dislikes are a clear signal of users' negative preferences, but if you sample fully from the dislikes, you could run into problems like folding in your offline models. So you need to you could try different sampling methods, whether sampling fully from unknown observations or for the negative samples, or sampling from a mix of unknown plus unknown plus clear negatives, or fully from hard negatives, and balancing this distribution is very important for the experiment.
Okay, here's, I think, the final question, which received a lot of votes is, does your network consider same-sex interactions?
No, this our setting is explicitly for opposite gender preferences.
Okay, I think we do one last one. Does the algorithm depend on context such as time of the day, holiday, or season?
Oh, yes. This we observed during one of our experiments during the Golden Week in Japan. We found a significant increase in activity of people, and our models had to be tuned even more further periodically to gather users' preferences. So that's why we reiterate it's important to retrain users' embeddings periodically based on not just seasons like holidays or public holidays or festivals, also different time period of the day and so on, where people are more active and not less active.
Okay, thank you very much. I think there's even more interesting questions there. I hope you can answer them in the Wova system. Yeah, thank you for the presentation. So this concludes our session, and I would like to thank all the speakers again for these great presentations, all very disciplined. We made it on time. This closes the session, and I think the next event then is the farewell, and hope to see you all there then. Have a good day.